Okay, time to get started. So now y'all may recognize this page. We were talking about this several lectures back. It was a while ago. So why are we doing it again? Well, I made a promise to y'all at this point, which part of the proof that I gave of this fact, right, is that the equation that we're trying to prove, well, my gosh, it's morally equivalent to an equation we have already proved. At least in the special case where you're talking about a linear transformation that can be represented by a matrix. And I just made this assertion that every linear transformation on a finite dimensional domain can be represented as a matrix. We didn't have the tools to demonstrate that at that time. But again, with that as an asterisk, you go through, that statement turns into this statement, which is already known, and we're done, and we've proved that fact, which had big consequences. Recall, this theorem led to this theorem, which led to our proof that the set of solutions to one of these differential equations is n-dimensional, and that's huge, right? This is one of the big theorems that allowed us to solve differential equations back in chapter 4. Right, section 4.2. Which was also, think about it, what did that lead to? Well, all the stuff that we did in section 4.5 about a mass on a spring and friction, and then correspondingly with LRC circuits, tremendous amount of applications, and if you trace it all back, it all comes down to this theorem that we proved with the asterisk. How do you know that every linear transformation defined on a finite dimensional domain can be written as a matrix, right? So this is a pretty big omission that I've been let dangle for a while, and now we're going to fill it in. It's an easy one to fill in. In fact, we did last time, and I just kind of forgot to mention it. But right here, so suppose you have a linear transformation, right? If this is a finite dimensional domain, then the point is you can just pick a basis, any basis. Doesn't matter. Pick a basis, right? Now you do need it to be finite dimensional so that your basis is finite so that it makes sense, right? We don't know what infinite matrices are. That's not a thing we want to sort of mess with. But finite dimensional domain, pick a basis. The target's going to be finite dimensional as well. Pick a basis for that target as well. And having done that, here's the matrix that represents that linear transformation. How do I know that matrix exists? Well, here's our formula for how to compute it, one column at a time. Right? So this calculation, not only does it let us, do some stuff here that we've, been playing with here in chapter 5, but this is that one little missing piece upon which so much other stuff has rested without our realizing it at the time. Okay, so I wanted to make that quick mention before going on. Now, last time we got through this part right here. I'm going to pick up there. So this next page of the notes is just it's kind of a for example. It's a little exploration of something that can come up in some circumstances. I think it's a valuable example, valuable observation. This is not taken from the book. This is my own example. So I'm just going to create a little scenario, and then I'm going to make an arbitrary statement, and then I'm going to show you how that might look, and more to the point, how it might look different depending on choices that you make about bases and languages and stuff like that. So here we go. Suppose you have a linear transformation from V to W. V is a vector space. Suppose it's got a couple of bases. Now, of course, there's, most vector spaces have infinitely many bases. R3, for example, here's a basis. There's a basis. That's a basis. There's endless. There's infinitely many bases. I'm just saying arbitrarily, how about these two? Let's just say. Okay. Now, you'll notice that one of them, the notation that I've chosen, makes it look like it's the standard basis. Let's recognize V is not necessarily Rn. We certainly are not going to assume that V is Rn. So the term standard basis really applies to Rn, right? It's literally the standard basis, consisting mostly of zeros, the occasional one. So V does not have to have a standard basis. If V is not Rn, then by this S1, I just mean some basis, maybe a basis that you find convenient. Right. Okay, likewise, W, vector space. Lots of bases. For example, maybe these two. Let's look at this vector right here, V1. I'd like to tell you what V1 is. How am I going to tell you what V1 is? We're in some abstract vector space. I don't even know what kind of abstract vector space. I can't really tell you about V1 in specific terms. Maybe it's a matrix. Maybe it's a function. Maybe it's a solution to some differential equation. I don't know, right? One convenient way that I can tell you what that vector is, or tell you about that vector, is describe it in terms of a basis. So you'll notice here, what I'm going to tell you about V1 is I'm going to tell you its coordinates. Coordinates with respect to a basis. Which basis? Well, the only reasonable basis about which I could tell you anything, and that is this other basis, the S basis. Okay, is everybody good so far? Okay, so V1's got some coordinates with respect to S1. Likewise, over here, that vector, W1, I'd like to tell you about it. I need a language with respect to which to talk about it. All right, so let's suppose I know a basis S2, and I'm going to tell you what W1 is in that language, namely by its coordinates with respect to that basis. Okay, likewise, I'd like to tell you about this linear transformation T. Again, if I'm going to tell you about T, I need to pick a language, or more to the point, two languages. So I could tell you about T, for example, with respect to these two bases, S1 and S2. Right? Pick a basis for the domain, one for the target, and you can write it as a matrix. Let's call it A. But I could just as well pick these languages, aka bases, and I could tell you about T, same linear transformation, in a different language, and I would describe it in a different way. Right? You pick these different bases, it's going to be a totally different matrix. Yeah. Okay. Same linear transformation. Okay, all right. Now, let the record show I haven't really done anything yet. I'm just kind of defining. I'm making stuff up and defining notation is all I've done, right? The goal of this example is to show you what notation can look like and to kind of give you a heads up for the kinds of things to be on the lookout for. So I'm going to describe a statement here. Now, I'm not saying that this statement is always true. I'm just saying here is a possible thing that might be true. Here it is, T of V1 equals W1. Again, there's no promise that, whenever you pick bases, this has to be true. Right? But let's consider if, hypothetically, T of V1 happened to be W1. Okay. All right. So now here's where it gets a little weird. With all of that context, I'm going to make the observation that these 5 statements here all effectively say the same thing. All 5 of these statements say T of V1 equals W1. Now, notice that one of them actually is T of V1 equals W1. Okay. So I want to show you, first of all, I want to persuade you that these 5 statements all do in fact say the same thing, and then I want to talk about how you can account for that. Let me make that point when I get to it. So first, let me persuade you these all say the same thing. I'm going to start by taking this statement right here, and let's just make the choice that I would like to describe this statement. I would like to enunciate this statement, but not in the abstract. I would like to enunciate this with respect to certain bases. I would like to say this in a certain language, you might say. And specifically, I want to say that statement in the language of the standard the S1 basis for the domain and the S2 basis for the target. Again, maybe they're standard bases, maybe they aren't. Okay. So that's a choice, and notice that's all that's happening here, right? in this statement just above that I have circled in blue. This still says T of V1 equals W1. It just says, but I want to talk about T in the language of S1 and S2. And I want to talk about V1 and W1 in the languages of S1 and S2. These say the same thing. This just does it in a language, and this does it in the abstract. Same thing. Okay. And then notice that having made these choices, having decided that I'm going to speak in S1, S2 language, notice that T is A in that language. Right? And likewise, notice that V1 has these coordinates in that language, those languages. And, etc. W1 has those coordinates in that language. So, I think this first one's a pretty easy pitch. Down at the bottom, this third line here is just a statement in the abstract, and this first line that looks cosmetically very different, it's really just the same statement, having picked a language. Okay. What about these other statements? What about these statements down here? How are these all the same? It's just, what do you get if you decide that you want to talk about this exact same statement in a different language? You don't have to always speak English, or you don't always have to always speak French, or, pick your language, you can say the same thing, it'll look very different in different languages. Here I'm just going to choose to speak a different language. So specifically, here we're going to choose to speak in these languages, V and W. And in the language described by these bases, V and W, this isn't quite all going to fit on the screen, but in the languages of V and W, T is just M. Right. Now, let's worry a little bit about the other thing down here. What's going on with these coordinates? Where did these coordinates come from? And this is just a clever observation. You should always be on the lookout for lucky breaks. But let's think about this. How would, if V1 is one of the vectors in this script V basis, here, let me zoom for visibility. If V1, being as it is one of the vectors in this script V basis, how would I find the coordinates of V1 with respect to that script V basis? And notice, that's asking the question, I have V1, I want to write it as something times V1 plus something times V2, right? Plus, et cetera, plus, plus something times Vn. And the coordinates that I'm looking for are just, it's the answer to this question. It's the winning move in this game. How do I write V1 as a linear combination of a list of vectors that includes V1? And the answer is it's an easy move. Right? I can win this game by putting an obvious 1 right there and then zeros everywhere else, thus giving me that the coordinates of V1 with respect to the V basis, 1 followed by a bunch of zeros. So heads up for this little trick. This comes up, you'd be surprised how often, that you're looking for the coordinates of a vector with respect to a basis that includes it. Right? And the coordinates are always going to be correspondingly, easy. Okay. Likewise, analogously, I'll say, for over here, how do I write W1 as a linear combination of a list of vectors that includes W1? Well, again, same trick. Okay. All right, so I hope that persuades you that all 5 of these statements are, in fact, equivalent. All 5 of these statements say the same thing. They do all look different. I want to draw your attention to these two. These two statements are on the list of 5 things that all say the same thing. So these two statements say the same thing, really, morally. They say the same thing. They look unrecognizably different. Right? One's talking about a matrix A and a couple of ordered N and M tuples with numbers C's and D's, and nothing of that is visible down here. Right, so here's what I want to encourage you to do when you see a statement like let's say this one, right? How could you recognize that in a different form? Say maybe like this. And the idea is as follows. Pick some aspect of the statement that's being made and try to understand from it what you know about it. What language is being spoken? I'll point out A here, for example. Right, I was given right here in the statement of this little exercise that A represents T with respect to a couple of given bases, aka languages. So that tells you what's going on. That tells you what language is being spoken here. So the fact that you've noticed that instantly gives you this. Okay. And then you could reasonably say, okay, well, T. Hey, what else do I know about T? Well, T can be described in another language. T can be described in VW language. Which gets us down to here. All right, let me zoom out so we can see all this at once. There we go. Okay. So that's just kind of, following the leads. A indicates a choice of languages and a linear transformation about which I know how to describe in other languages. It seems like a reasonable thing to write down. Then you can continue to pull on the threads and say, okay, well, look, I'm speaking here in the domain. I'm speaking in the language of S1, and I could reasonably ask the question, this collection of numbers, what vector does that represent in S1 language? Well, again, given. And that makes you notice that we're talking about V1. Likewise, here that we're talking about V2. Once you realize what you're saying in abstract terms, and once you realize that, if you've decided, for example, that you want to say all that instead in a different language, well, then you just have this task of figuring out, okay, well, how do I write V1 with respect to the languages that are dictated by this choice? And there you go. And we've already talked through that business. So, when you see statements about matrices and what I'm going to loosely call vectors, let me say it as when you see statements about matrices and Euclidean vectors, henceforth, I suggest that you look at that with a raised eyebrow and think, okay, listen, that's just a shorthand. That's a choice that's been made to think about something abstract, but in a certain way. Try to identify what are the languages in question. What is the abstract statement underneath it that's really being talked about? Think about it in those terms, and then think about that in different terms if necessary or convenient. Okay, all right. This is all going to come naturally to you eventually. I mean, eventually is a open-ended term. This is a fairly weird way of thinking, right? And I grant that, right? But it's a good thing to try to dwell on. At this point, I mean, I've been doing this for a long time, but when I see a matrix, I mean, I instinctively go up and ask, what are we actually describing here? Matrices are not really usually the thing of interest. It's usually what do they represent. That's the thing of interest. So try to push yourself to thinking in those terms. Okay, moving along. Change of basis is a clever idea, reasonable question we might ask. Suppose I have a vector. Well, more specifically, suppose I have the coordinates of a vector with respect to, let's say, the script V basis. And suppose that I would like instead to have the coordinates of that vector with respect to a different basis. Now, I emphasize the question here presumes that we are not changing the vector. Same vector. Right? The abstraction that I'm trying to understand is not changing. I just want to understand if I were to, if I knew it in V language and I want it in W language, how do I translate? Is there a little mathematical sort of dictionary you might say, for between these languages. Turns out, no big deal. It turns out that's exactly what's represented by this diagram right here. Notice, again, we're not changing the vector itself. The action of not changing the vector is described by this linear transformation. Right? This I is called I for identity, means we're not doing anything to the vector at all. And notice that the coordinates with respect to the script v basis are down here. The coordinates with respect to the script w basis are down here. And if I would therefore like to know how to convert script v coordinates into script w coordinates, I just want to find that. I just want to find the matrix. This is a little strange. I want to find the matrix that represents the action of doing nothing. Right? I want the matrix that represents the identity transformation, but very critically, where the input basis and the output basis are different. All right, so the good news is that we already have the answer to this. We have a formula for how to find a matrix representing a linear transformation. Right? We understand matrices by columns. The columns of the matrix that we're looking for are obtained by that formula that we saw last time. Specifically, recall that you take these vectors, right? You put them into that transformation, and then you write the output from that in that language. Right? The standard Patt formula that we proved last time. Conveniently, of course, the action of not doing anything to the vector means it's just that same vector. Right? So, nice formula then for doing a change of basis matrix. If you want to find this change of basis matrix, even simpler formula. Take these input basis vectors, write their coordinates with respect to the output basis, and these are your columns. Okay, everybody on board? That's just immediate, like I say, immediate consequence of a formula we already knew. Okay. Notice as well, by the way, I guess I kind of skipped over this. What that means then is that this change of basis matrix, this matrix is what you can multiply by, what you can multiply by the script v coordinates to get as a result the script w coordinates. Okay, let's see an example. Let me do this first. So here we go. A couple of bases. This is in R2. By the way, this is a starter example. Let's consider vectors in R2. Here's a couple of bases for R2. Notice one of them is the standard basis. Now, in order to be able to get anything done, I need to tell you about these vectors. For example, V1. I got to tell you what V1 is. Awkward. How do I tell you what V1 is? I have to tell you based on its coordinates. Okay, but coordinates with respect to what? Right? So the way I'm going to tell you what V1 is I'm going to tell you its coordinates with respect to the standard basis. So that I want to point out that you just got to be careful when you're thinking about a vector as coordinates. Implicitly or otherwise, there is a basis with respect to which you're talking about those coordinates. So I'm just being explicit here that I'm describing V1 by its coordinates with respect to the standard basis. By the way, just for your so you know, just for your information, sometimes people you've seen this a million times, people will write V1 equals 1, 1, and not explicitly indicate what basis is being used. And in a lot of contexts, it's fine, right? I mean, if you're doing math where, everything's being described with respect to the standard basis, why do I have to? It's the brackets every single time. It just gets tedious, right? So if it's perfectly clear what basis you mean, fine, no problem, right? If it's not perfectly clear which basis you mean, then this is a little not, it's a little suboptimal, right? And it'd be better to explicitly indicate what basis. That said, it is still the case that sometimes people will write this and leave it to the reader to infer. Okay, well, yeah, but when I don't say that, I mean, of course, with respect to the standard basis. So anyway, I prefer that we do this, but I accept that this will also happen. Okay. So let's, with this being given, these two vectors, there they are. What's the change of basis matrix? Here's again our Patt formula for the change of basis matrix. The columns are what you get by taking the input vectors and writing their coordinates with respect to the output basis. Right, our Patt formula for how to write down a change of basis matrix. Notice, as it turns out, those happen to have been given. I mean, lucky break, right? What we needed is exactly already known. And likewise here, this is exactly one of the things that was given. And so here's our change of basis matrix. Now, what does that mean? I mean, in practice, how do I know this is right? Let's see, what does this matrix actually do? Remember, what it's supposed to do is this is a matrix that you're supposed to be able to multiply by script V coordinates, and what comes out is supposed to be script W coordinates for the exact same vector. And I just want to show you a sanity check. This is just a, let's just kind of see it in action. Sorry, I wanted to keep this a dark color. Here we go. So change of basis matrix. Does this do what it's supposed to do for the vector V1? Does this matrix turn script V coordinates of V1? By the way, it's another one of those freebies. How do you write V1 as a list of coordinates with respect to a basis that includes V1? Easy one. So does this matrix turn, as it should, script V coordinates into script S coordinates of the exact same vector, which, again, given, right? Script S coordinates, we know are that. Does this matrix do that? Does this matrix multiply by this list of coordinates to give you that list of coordinates? Do the arithmetic. You can do it on your own. Sure enough, it works exactly as it's supposed to. Okay. Likewise for V2, right? The same matrix, change of basis matrix, turns script V coordinates into script S coordinates for V2. Again, this was given and that was given. And the matrix does multiply as it's supposed to. Okay. How we doing? Everybody on board? Good news, it's highly algorithmic, right? Again, here's our formula. Just make sure to understand what this formula does for us, right? Realize what that change of basis matrix does is it changes the basis with respect to which we're talking about vectors, right? So it changes from, V coordinates to W coordinates. It doesn't change the vector at all. Nothing's actually happening to the vector. It's the same vector in as it is out. We're just translating it into a different language. All right, now I have to talk about a unfortunate... Oh, I'm sorry, I got ahead of myself. Super quick point. If you want to change from W to V, and you want to know how does that relate to changing from V to W, I think it's a pretty easy pitch that if you convert and convert back altogether, you've done nothing, right? I think that's an easy buy, right? If you start with W coordinates, turn to V coordinates, then turn those V coordinates back to W coordinates, nothing happened. So these two matrices, their product is the identity matrix, and therefore they're inverses of each other. So I think that's an easy pitch. Okay, so now, awkward conversation. Apologies for this. Let's, again, let me remind you, what does our matrix here do? Here it is. This matrix, for which we have this formula, oh, come on, turns v coordinates of a vector into w coordinates of a vector. Doesn't change the vector at all. Right? Just changes the language that we're talking about it. Okay, so I call this, and I think this is reasonable, I call this the change of basis matrix from v to w, right? Look, we're starting with v coordinates, and then we're ending up with w coordinates. So from v to w. Yeah. I mean, perfectly natural. The book doesn't call it this. This is really unfortunate. I don't know what to tell you, but the book calls this matrix, using this notation, exactly as I am, using this formula for it, exactly as I am, applying it in equations, just like I am here. The language that it uses to describe this matrix is that it's the change of basis matrix from W to V. Isn't that weird? My opinion. I think that's weird. Now let me. I like to get everybody on my side first, and now let me show you the point of view that the book takes. Well, correction, a point of view that would justify what the book is doing, and that is, let's look at this equation. This is a true equation. It's a matter of writing it down. You can totally prove this with the algebra. In fact, here's an easy way to do it. We know that this column, for example, well, it's a linear combination of these columns where I use these numbers as coefficients, right? And let's think about that multiplication. I'm taking these columns that are the W vectors. If I take a linear combination of them, using coordinates which are exactly the coordinates of W vectors that would produce V1, well, no surprise, you produce V1. Right? Likewise for these other columns. This, like I say, is true algebra. And if you think then about, okay, well, how would I interpret, given this equation, how would I interpret what this matrix is doing? Note, that's the exact same matrix as above. Exact same notation I'm going to therefore use. Notice that what it does is it turns the W's to the V's, and thus there's a point of view there that this matrix, purple matrix, it's a change of basis matrix in a different sense. It's not changing the basis that we're using as a language to describe other vectors. It's changing the bases themselves. It's going to turn this list of W vectors into this list of V vectors. So, okay, fine. There is a point of view there. And what we have then is just a truly unfortunate situation that this matrix, let me zoom out, this matrix here, same exact matrix, does do different things that seemingly go in opposite directions from each other. So here's the thing. What we're going to be doing in Math 216 is we're going to be doing this. We're going to be thinking about taking a vector and rewriting that vector with respect to a different language. We're going to be doing a lot of this. So I'm going to use this terminology, change of basis matrix from V to W. Right. This business down here, motivating the other terminology, the terminology that the book uses, we're going to be doing zero of that in Math 216. Right? So I think it was a pretty strong argument for us to use the green terminology. Now, I want to recognize that this is an awkward circumstance, right? It is unfortunate that I'm using language then in a way that is diametrically inconsistent with the way the book uses language. So, heads up, right? As you're reading the book, be on the lookout for that source of confusion. Likewise, on the homework exercises, you've got to watch out for the book's use of language in this way. I can tell you exactly where it's going to come up. This is section 5.3, exercise 1. In section 5.3, the book is going to use language analogous to this language here, and it's not W's and V's, it's like alphas and betas, and I don't remember which way it goes, whatever. But the point is, they use the language, change of basis, matrix from, and then they enumerate, in English, as it were. So just realize, when you read that, you should interpret it the way that they intended it. Right? I want the question to work out the way that they intended it, therefore you have to interpret it the way that they intended it. And that's the only place in this course that you should interpret the language that way. In all of my old exams, I mean the green language. Right? All of my old exam questions, when it's written in English, I mean this. In all of my future exams, if I use this language, it will mean this as well. Okay, and I saw a hand over. Oh, yeah. So do it this way. I just think this is overwhelmingly the most natural thing for what we're doing. Yeah. Okay. Alrighty. And by the way, just for your information, I mean, this is something that comes up in other contexts in math. It's just not something we're going to do anything with in this course. Okay. And then one other thing. So, outside of Math 216, I don't know how you're going to see it. Right? It could sort of be either. And it makes, as you see from these two choices, right, it makes more sense to do it one way versus the other way depending on the context. So when you see language of anything, of either of these sorts, change of basis, matrix from, in English, don't just assume that it's one way or the other. Right? Don't cite me as the authority. I mean, it depends on the context. Right? And even the notation, even this choice of notation. Now, I'm doing exactly what the book does here, which is fine with me, that the input basis is on the bottom. Right? Well, that might not be the same in the different books. They'll make different choices. They might not write it like this at all. They might have a completely different notation. So don't assume about the notation. What you can always take to the bank is if they're going to use a matrix like this, they're going to do something with it. And if you see this, right, then you know that they're talking about this in the sense that you would like to think of like that. Right? So trust the equations. Don't trust the notation. Don't trust the language, for crying out loud. Right? Trust the equations of what the things are actually doing. Okay. All right. Enough of that. Okay. What about for linear transformations? Apologies for the big scary diagram that I'm about to show y'all. It's not as bad as it looks, but let's look at this circumstance. What if you have, now just bear with me here, what if you have a linear transformation from V to W? Here we go. Linear transformation from V to W. What if you know how to write that linear transformation with respect to one pair of bases? Now keep in mind, the way we write a linear transformation with respect to a pair of bases is we make a little diagram where we have a change of basis matrix on the one side, also on the other side. We're looking for the matrix such that down and over is the same as over and down. Right? So this diagram, including this vector, this arrow at the bottom, is how we think about T from the VW point of view. And suppose you would like to figure out how to represent that same linear transformation just with respect to a different pair of bases. Okay, well now what that says then is I just want to understand this diagram, the yellow diagram. Note it's the same linear transformation. So these two rectangular diagrams, they're not just floating over here independent of each other. They meet at the top because they're describing that same linear transformation. But different bases over here, different bases over there. So there's the question. If I know blue, how do I find yellow? Then I'll notice that that's just a change of basis diagram. Not doing anything to the vectors, just thinking about the same vector with respect to different bases. This is a change of basis diagram. Right? So altogether, everything in this diagram, now that's a scary looking diagram. This may be your first time to see a diagram that doesn't actually fit on paper. It's really a three-dimensional diagram. Right? It's horrifying. Right? But notice everything in that diagram is stuff we've already talked about. Right? And so I hope it comes as no surprise. The way we do this is, let's just kind of walk through it. If you want to know that matrix, well, first, do a change of basis from V prime coordinates to V coordinates. Do the linear transformation starting in V coordinates, as you already know how to do the linear transformation. Starting in V coordinates. Note that what comes out is in W coordinates. Well, wait a minute, that's not what I wanted. I wanted my output, I want my output to be in W prime coordinates, not W coordinates. So then, convert from W to W prime coordinates. So if you know green and you want purple, well, okay, purple is just this composition of doing that three-step succession of matrices. So it turns out it's not that bad, right? I mean, it's a sort of a nice punchline. Yes? Oh, yeah, no, right. It's a great question. So let me zoom in on that. So yeah, you certainly could, for example, so here I made this one double-headed because I'm not really going to be doing any of that in what we're doing. You could take coordinates and infer the vector, or you could take the vector and infer coordinates. A basis goes either way, right? And that's kind of true here as well. You could go either way with this. It's just that in our application, we're not going to. Right? In our application here, you can see in how it turns out. What I'm specifically going to do is go that way as part of my process of going all the way around. And so, even though you're quite right, yes, there is a change of basis matrix from V to V prime. I don't need that change of basis matrix from V to V prime. What I need is from V prime to V. So I only drew it the one way. Yeah, but if you want to make it go the other way, you can. It just won't be useful for what we're doing here. Yep. Okay. All right. Now I'm going to show you an application of this. By the way, before I do the application, a real quick observation. You can think this through without actually drawing the diagram. Right? I mean, you can say, hey, someone's going to come to me with V prime coordinates, and they want me to do the linear transformation, and they want me to give the results in W prime coordinates. Well, look, they're going to come to me with V prime coordinates. Okay, I'm going to take those V prime coordinates, I'm going to translate them into V coordinates. Having converted to V coordinates, I know how to do the linear transformation T here. The output's going to come in W coordinates. Oh, wait, they wanted W prime coordinates. Fine, I'll translate again. You could just think it through kind of as a three-step process, right? And that's fine. That said, I want to encourage y'all to think about the diagram anyway because of the following. And I've done this with test questions before, and the reason I've done this with test questions is because stuff like this comes up in the real world sometimes. Suppose that I give you this. Right, as a given. So I tell you what that vector is. You know, the W coordinates of T of some given input vector, whatever that is. Suppose I give you that output. The question could then ask, compute this. Right? I could say, multiply the T V prime W prime matrix times the V prime coordinates of that same vector V. Well, the way you would write this down in the algebra and the way that you would write that down in the algebra will not look particularly similar. Right? But if you see the diagram, if you have a picture of the scenario that you're looking at, what you see is, okay, well, I was given this, and I want this. How about I just multiply by that change of basis matrix? And it jumps in the boat, right? I mean, it becomes an easy problem if you take the point of view of the diagram. It's a really hard problem if you insist on doing it with algebra alone. So, heads up for that. Okay. All right. Couple of examples on the next few pages. I'm going to skip this next example because it's not quite as challenging as this example, which is very, very similar. So I'm going to do this second example. I leave the first one to y'all to sort of think through on your own. Here's the idea. Suppose I want to find a matrix B that has these two features. I want the matrix times 1, 3 to be 3, 2, and I want the matrix times 2, 5 to be 4, 3. I mean, how would I find a matrix that does this? So the point of view I want to show you is, step one, keep in mind, when you see algebra like this, going forward, I encourage you to think that, look, this is given as a statement about a matrix and some pairs of numbers. But come on. This is really representing a linear transformation. These are really representing vectors. They're not just ordered pairs of numbers, they're vectors. This is really a linear transformation. Let's think in those terms, in the abstract, independent of coordinates. And then having done that, we have the flexibility to choose whatever coordinates might be convenient for our purposes. And having that additional flexibility is going to pay off. So first observation, look, B, it's going to represent some linear transformation. Let's view this as representing some transformation S in standard coordinates. It represents some linear I don't know what S is, but it represents some linear transformation S. Likewise there. And let's see here. There's a bunch of vectors then that I need to talk about. These two vectors and these two vectors, what do these represent? Well, they represent something in standard coordinates. The green ones represent... I'm sorry. I circled wrong. Sorry. My apologies. These two green vectors represent a couple... They're inputs. So they represent a couple of vectors in the domain. And these two vectors here are outputs. They represent a couple of vectors in the target. Now, I'm just going to give them names. I'm going to call the green ones V1 and V2. And I'm going to call the blue ones W1 and W2. Right, so now, having made those choices, right, I can rephrase my original question from I want to understand these matrix equations to instead I want to understand these linear transformation equations. Right? The equations as given, I was rigidly confined into thinking only in standard basis language, which is very restrictive. And now, I'm free to choose whatever basis I like. And I'm going to choose selfishly as follows. Right? Let's imagine that I could come up with a couple of bases, script V and script W. Let's suppose I could figure out what that matrix is, and I'll talk about how to do that momentarily. If I understood this matrix, notice I can find the matrix that I actually want just by doing a change of basis, right? The change of basis process that we talked about on the previous page, it's just a matter of multiplying by a couple of matrices. Change of basis is easy. Right? So let's think in terms of understanding S with respect to convenient coordinates. And then, we'll convert back to with respect to the coordinates we need after we're done with the convenient work. Okay. So what makes for a convenient basis? Well, whatever I pick for this input basis, I'm going to have to put into the linear transformation S. Check it out. V1 and V2. I know what happens. It's conveniently given to me what happens to V1 and V2 when I put them into S. So that motivates me to pick this basis consisting of V1 and V2 for my domain. And then now let's see, hang on a second. Whatever comes out, those outputs I'm going to have to write in terms of script W. Can I think of a basis with respect to which it's easy to talk about W1 and W2? What basis would be convenient for me to talk about W1 and W2? Well, again, being as greedy as I can think of, it sure is easy to talk about W1 and W2 with respect to the basis consisting of exactly W1 and W2. Again, I'm being super greedy here. Right? So, the fact that I'm given this information suggests that I should think in terms of these bases, at which point, one at a time, take the V vectors, do S, write in W language. These columns are real easy to write down. 1001. Then we just have to do a change of basis. Now, to do this change of basis, I need change of basis matrices from S to V and from W to S. W to S, we know. S to V, well, this is the inverse of a matrix. It's easy to write down. I know how to write down the matrix from V to S because I know the vectors from V in S language. This is just the inverse, then, of the one that I know how to write down. And again, a little bit of algebra, and that's something you can figure out as well. Like that. And then arithmetic, and we're done. So it's a really powerful argument. We turn a seemingly hard, I'll call it high school algebra problem, into, with sophisticated tools, we turn it into a trivial linear algebra problem. The big trick, of course, being pick the right bases, think greedy, find the bases that make your life as easy as possible. Make that choice. Okay, see y'all later. Have a good weekend.